Hello and welcome to TI Precision Labs. In this series, we're going to discuss 25G Ethernet transmitter optimization. In future sessions, we'll cover other aspects of 25G data transmission. First, let's introduce the key terms associated with transmit equalization. The waveform shown here first contains the bit sequence 00111. Let's start with voltage point V1 on the left. Whenever there is a 0 to 1 or a 1 to 0 edge transition, the bit period right after it, for example V1 and V4, is known as our post-cursor. To provide high-frequency boost to the post-cursor component of our waveform, de-emphasis may be applied to the subsequent bits further from the transition. By reducing the amplitude of the non-transitioning bits, the low-frequency component of the signal, relative to the post-cursor transition bit, high-frequency boost is effectively applied. The bit preceding the edge transitions, such as voltage points V2 and V3, is known as the precursor. Precursor de-emphasis may also be applied to equalize the transmitted signal. The precursor and postcursor de-emphasis functions allow the host system to pre-distort the transmitted signal. The objective is to obtain an equalized electrical signal after transmission across media suffering various signal dispersion effects. To calculate the amount of pre- and post-cursor de-emphasis in decibels, we simply take the ratio of the post-cursor or precursor voltage amplitude over the amplitude for the non-transitioning signal portion, either 20 times log V3 over V2 or 20 times log V1 over V2. The figure here illustrates the block diagram of a 3-tap finite impulse response filter, or FIR. This architecture is commonly used in electrical interfaces as well as physical interfaces in telecom and wireless equipment as prescribed by the Networking Industry for Ethernet, IEEE. An FIR is a discrete form of equalizer, and each FIR tap carries a delayed and scaled version of the input data. The FIR then pre-distorts the TX output signal by adding back these tapped signals to the output, with the result being an equalized output signal. The FIR filter can be used to compensate for either precursor or postcursor inter-symbol interference on the signal. Now let's focus on 3 signal impairments due to the transmission media and examine how our transmitter optimization helps. The first impairment we'll cover is insertion loss. Insertion loss corresponds to higher signal attenuation observed on higher frequency components of a signal relative to the lower frequency components. The graph on the left tracks insertion loss over frequency. Note that this graph shows an additional -5 dB shift for the blue 10G lines in order to better visually compare the two systems. At 25 gigabits per second, the insertion loss is at about -15 dB, while for 10G, this is at -3 dB. A 5-fold difference. Therefore, transmitter optimization parameters need to be fine-tuned to overcome the 15 dB loss we see when signaling speed is higher, such as 25G. To compensate for insertion loss, post-cursor boost is shown to be the most effective method. Let's face it, for high-frequency signals such as 25 gigabits per second data, every element on the signal path, component landing pads, board traces, adjacent signals, etc., all play a role in the signal characteristics. To make this clear, let's take the simple example illustrated on this basic circuit block diagram. Here we have 2 adjacent AC electrical sources, each launching a signal into the transmission line and subsequently onto an output termination. For either signal, reflections will occur to the extent that the transmission line impedance and output load resistance do not match. Poor transmission channel design, or the presence of parasitics, can lead to such undesired impedance variation. In addition, at higher signal frequencies, it becomes more likely for signals to couple between adjacent data channels, primarily due to parasitic effects. This signal impairment effect is known as crosstalk. The use of large signal swings, usually to compensate for lossy transmission media, and signal reflections can further increase the likelihood of crosstalk. Here we have the differential S-parameter transfer function, SDD21, i.e. the insertion loss plot, for a few example test channels. A couple of key observations can be made from the plot. The first one is that, while the plot shows a smooth and monotonic trend for frequencies below 12 GHz, the plot behaves less monotonically at higher frequencies. The second observation is the presence of ripple at higher frequencies. These effects stem from parasitic effects, like parasitic capacitance or inductance, that become more prevalent at these higher frequencies. The observation of these effects on the insertion loss plot often correlates with the occurrence of reflections and crosstalk at higher frequencies. Our third transmitter impairment, which is more significant at the 25 gigabits per second data rate, is precursor dispersion. One simple way to illustrate the precursor effect is by examining the response of a pulse launched across a channel for both 10G and 25G data rates. While at 10G, the precursor ISI, measured as the signal amplitude 1 unit interval before the pulse peak, is effectively zero. For 25G, there is significant precursor ISI present. What this means is that a data bit is spreading in time in such a way that it interferes with the adjacent bits being transmitted. If not compensated for, this signal effect can lead to transmit data bit errors. Now, on this slide, we illustrate a couple of 25 gigabits per second eye diagrams, corresponding to a signal after transmission across a 6 dB insertion loss channel. Remember, an eye diagram illustrates all the possible bit transitions for a transmitted data pattern. Two key metrics for assessing eye quality are the vertical eye opening and the horizontal eye opening. The bigger the eye openings, the more margin the transmit data has to bit errors. The eye diagram on the left is for the case where there is no precursor or postcursor applied. The eye diagram on the right is for the case where both precursor and postcursor boost are applied via FIR de-emphasis. Thanks to the FIR equalization, the right side eye has a 38% larger eye opening and thus that much additional link margin. To refresh your mind on what we have discussed, let's have a short quiz. Which FIR tap best helps to compensate for insertion loss? Precursor, postcursor, or both? The answer is postcursor. Precursor dispersion is higher at lower data rates. True or false? The answer is false. Precursor dispersion is higher at higher data rates. Which signal impairment is usually worse at 25 gigabits per second than 10 gigabits per second for a given channel? Insertion loss, crosstalk, reflections, or all of the above? The answer is all of the above. In closing, I'm glad we could bring you this 25 gigabits per second transmitter optimization module. In future sessions, we'll go into more details related to the 25G retimer function, and we'll cover more parameters affecting high-speed signal conditioning.